Okay, we can get started. Hello everyone, welcome to today's iStructE webinar in collaboration with StatiCa, which will be on castellated beams and overcoming design limitations with CBFEM. We have Theo and Costas with us presenting the webinar from StatiCa, who I shall hand over to. You'll have the opportunity to ask them questions at the end, and I'll be sending your CPD certificates once the webinar finishes. Thank you very much. Over to you.
Thank you, Merce. So good morning, everyone. Welcome to our third webinar in cooperation with the iStructE. As with the previous ones and the upcoming ones as well, the goal is to educate structural engineers about new technologies and processes for the design of structural steel, details and members. The theme for this webinar is castellated beams and how to overcome the design limitations. Castellated beams are being used extensively in the UK, but also in other parts of the world. But there are still areas where, in terms of design guidance, that are not covered, leading to limitations in their application. So we hope that with this webinar, we will shed some light on these limitations, but more importantly, how to overcome these limitations with CBFEM. Before we begin, let me just quickly introduce myself. I'm Theodore Tsirozidis. I'm the Managing Director of StatiCa UK. And with me is Kostis Hatzopoulos, who is our Technical Manager and is going to do the presentation. For those of you who haven't used GoToWebinar before, you will see on your right side of your screen a panel. You can hide this panel if you want to, and you can also use this lower part of this panel to ask any questions you may have during the webinar. We will have a little bit of time at the end, so feel free to send us anything you want. And we will make sure that we will answer all of them, either during the webinar or at the end, or maybe after the webinar through email. So before we actually start the presentation, I wanted to make a quick poll just to understand more about the challenges that you have, the challenges that you're facing when you're designing castellated beams. So I'm going to quickly run the poll. So the questions are, the question is, what are your challenges when designing castellated beams? Is it complex cross sections, or for example, build-up section? Is it complex configuration of openings? Is it complex opening shapes or complex loading conditions? Of course, if you don't design castellated beams, you can choose the last option. So please let us know what are your challenges. I'm going to leave it for a few seconds. I can see that a lot of votes are coming in already. Very good. Thank you very much. I can see that we have pretty much all sorts of answers. I can see that one is getting a little bit more. Very good. I think most of the people have voted, so I'm going to close the poll and show you the results. So as we can see, the results are pretty much divided into the different answers that we have. So most of the people actually facing challenges were when it comes to openings, so complex configuration of openings. And then we have obviously lots of people do not design castellated beams, but also complex cross sections. So we have a variety, let's say, of answers. So that's good. It's good to know that most of these things are actually indeed challenges that you're facing. So I'm going to quickly go back to the presentation. And with this, I'm going to switch over to Kostis, who is going to do the introduction and the rest of the webinar.
Thank you, Theodore. Just give me the presenter so that I can share my screen with you.
Okay. And I think we can also close our webcams just to save some bandwidth as well.
Okay. So just confirm that you can see my screen.
Yes, perfect.
Good. So I would also like to welcome our attendees, and without further delay, move this webinar where we will discuss beams with web openings. So as an introduction, the beams with web openings that are also known as castellated beams or cellular beams have become a very common requirement in construction projects because they have a very big advantage, and the advantage is that they allow the incorporation of surfaces into the structural height of the beam, and they can essentially hide the surfaces into the ceiling, which leaves clean space that the architects love so much. Roughly speaking, castellated beams are long span members, having large, regular openings within the web depth. And in this slide, I have two example pictures that I have taken from Steel Construction Info website, and both structures are fabricated from Glockner Weststock, a company that is also well known also for the fabrication of these beams. So moving to the next section, I would like to make a short introduction to the design guidance that is available up to date for these components. Despite the convenience provided by this structural system, its use requires additional design considerations that are unfortunately not covered in the code text. For the sake of completeness, I must mention that a draft amendment was prepared for the Annex N of the pre-standard Eurocode text, ENV 1993, for the design of beams with openings. However, this was never added to the code text. As such, the SCI published an excellent guide to fill this gap. This guide is displayed here and is called The Design of Composite Beams with Web Openings, and it's also known with its code name P355. This guide is unique, and I strongly recommend it to anyone interested in designing beams with openings, as it provides a solid foundation for the design of this system. So according to this guide, the design of such beams is governed by the so-called Vierendeel or four-corner bending, which is the result of the presence of openings in the web of the beams. Since a major part of the web is lost, the overall beam shear resistance is locally reduced, and this is the reason This is also the reason that this effect is created. And on a separate note, this is also the reason that we need to position openings away from high shear zones, and these high shear zones are usually located at the beam end. The design rules given in the SCI publication are valid for beams with rectangular, circular, or elongated circular openings. And according to the guide, again, it is also essential to maintain a uniform web thickness. And I'm saying this because we can also create beams from by welding two different cross sections, and the web thickness may vary along the height of the beam. Although the problem is well defined, and a lot of work was done to extend previous guidance from the SCI again, it is clear from the text that a lot remains to be done from the designer, as the designers need to consider the correct deflection calculation for cases other than a uniform load, the central point load. Designers need to identify specific cases and apply the modified design provisions, which may be significantly different between design iterations due to geometry changes, especially in the location and the type of the openings. We also need to carefully consider the influence of openings at the end posts at the high shear zones, where besides the high shear forces, there is also potential interaction with the type of the connection. Lastly, in case that openings are created in existing structures, there is always the danger that these openings may lie outside the limits of the guidance due to accidents and construction failures. So at this point, let's move to the design of castellated beams with a new method called the CBFEM. In this webinar, we will not dive into the details of this method, as we have already prepared the course that will be available for free in YouTube. In a nutshell, CBFEM is a finite element generalization of the component method used in Eurocode 1993-18 that was originally meant to deal with joints. However, CBFEM is not an arbitrary application of finite element analysis. It is a design-oriented method, which means that it provides very good agreement with the results of referent calculations. To do so, the method is methodologically verified and validating, ensuring that it can adequately predict the behavior of the assessed structural part. This is a very important step that is usually skipped from inexperienced analysts, and is also the reason that experienced engineers do not blindly trust results from an arbitrary finite element analysis. However, CBFEM has gone through extensive validation and verification, and the application of the method requires tools that, depending on the modeling choices made by the designer, can automatically transform the structural description to a finite element shell model created from CBFEM components. Briefly, what we call CBFEM components are fine-tuned finite element sub-models that reflect the behavior of plates, bolts, welds, and other components described in the code. And we have proved that these finite element sub-models, or CBFEM components, provide very good agreement with the code. In this webinar, I will demonstrate and compare the design of castellated beam following the worked example illustrated in the SCI guide, where the design of a composite beam is performed according to the rules prescribed there. In this example, the adequacy of the 10-meter span composite secondary beam with web openings is verified. It is subject to imposed uniform load. It has two circular openings on one side of the midspan and two rectangular openings on the other side. One of the rectangular openings is stiffened, and in the worked example, the adequacy of both the final and the construction stage is verified. Due to time constraints, in this webinar, we will look and compare the results for the construction stage. The chosen beam is a UKB 457, weighing 74 kilograms per meter. The steel grade is S355, and the span is 10 meters. So at this point, let me move into IDEA StatiCa member, which is the tool we have that implements CBFEM for members. Here, I will create a new project. I will go with the S355 steel grade, and then I will create a 10-meter span. I will then select the beam section, accept this, and create a project. In this, okay, let's also type the name of the project. I will create a new project, okay? So in this model, we can also account for the direct influence of the lateral beams at the columns, or even secondary beams that connect to our analyzed member. Of course, this is not the case in this webinar, so I will be removing this beam here. So this beam, and since this beam is hinged, I will also rotate the columns so that it is connected on the weak direction of the eye sections. Another important aspect of this model is that the supporting members are also partially connected, and we're able to in that way, we're able to reproduce the influence of the member and their connection. In an actual project, we could potentially load these members along the height and even at their ends to approximate as close as possible the stress state of the global analysis model where this submodel belongs. Now that the columns are oriented as expected, let's go and define the openings in the beams. So I will firstly add the rectangular openings. I will define the size. They have a width of 500 mils and a height of 300 mils according to the worked example. I can also define a rounding radius, and I will move them in place away from the high shear zone. And I will duplicate this one. So my rectangular openings are there. I will add circular ones. Diameter of the circular opening will be 300 mils, and it will be positioned to the other side of beam. Again, I have two openings. We have a distance of 450 mils. So the openings are there. I also have the option to easily add ring stiffeners stuff, but however, I will not do this right now. And now that the geometry is almost ready, I need to connect the beam to the column in a way that ensures the pinned behavior required by the worked example. To do so, I will start from the left side, where I will define connection. In this case, I will use a thin plate connection. So let's add a thin plate connection, which will also be pre-designed. Let's also switch to this transparent view. I'm not having a notch, and I want the gap of 15 mils here. There it is. So the connection is applied on the model, and now I will duplicate it on the other side. Beam is ready to be loaded. Now let's move back to my slide to assess the beam during the construction stage. During this stage, a uniform load of 5.49 kilonewton per square meter is applied. This load probably refers to an effective width of 3 meters, which makes final value of 16.47 kilonewtons per meter. So let's go and apply this value. One thing that is important is that in the CBFEM context, I can apply a combination of line loads, point loads, and forces at the different member ends. So I'm not limited by the loading. Since there is an underlying finite element model, this load has dimensions. So the minus 16.47 kilonewton meters is applied at the top. I also have the option to apply at the bottom, etc. And it has a width of 190 mils. So this is applied at the top of the beam. The definition of the load location should be familiar to any one of you that has checked steel members for lateral torsional buckling, where the load position is also important for the calculation of the M critical value. So first load is in place. Here, let's move back to my slides, where I have also detected the deflection calculations that are relevant to this member. In the construction stage, we have a total load of 2.85 kilonewtons per square meter along the effective width of 3 meters, which gives a total value of 8.55 kilonewton per meter. And this value corresponds to a deflection of 15.9 millimeters. However, in order to account for the influence of the openings, this value needs to be corrected, and it needs to be increased with a factor that I have detected in another calculation. So the final value of this deformation, the corrected value is 17.20 mils. So let's move back. I will create another load case where again I will add another live load. The load will be applied at the member top and have a width of 190 mils. The model is now ready to be solved. I will press the calculate button and the calculation process starts. And during this process, the CBFEM cell element model is automatically created from this substructure description I have provided. This CBFEM model contains every aspect of the structure, including fin plates, nonlinear beam elements for the bolts, interpolation constraints for welds, etc. The analysis just completed, and the analysis that was completed is a materially nonlinear analysis according to the provisions of Eurocode 1993-15, Annex C. The application of these provisions is one of the things that makes the CBFEM code compliant. To perform this initial analysis, and according to this part of the code, an elastoplastic material with a nominal plateau slope was adopted. You can see the respective material law highlighted in this slide. And according to the code again, for the ultimate limit state and for structures that are not susceptible to buckling, I emphasize this as I will return later on this condition. We just need to ensure that the principal plastic strain is limited below 5%. Now, this is a very convenient ultimate limit state verification because the check of any part of the substructure becomes independent of the substructure overall geometry and the location of the check. This means that the ultimate limit state verification is identical for every part of the model, and we don't need to look for specialized formulas that apply to a specific case. For example, it doesn't matter if you check the equivalent T over an opening, or if you check the unperforated part of the beam, and it doesn't matter the shape of the opening. This simple check is identical for every part of the structure, meaning that you can use it to check everything in the model. Let me jump back to the calculated model, and as the analysis is completed, the graphical view switched to the principal plastic strains, where we can see the model colored depending on the strain state of each part. Color is gray, which in this case means that gray parts remain in the elastic area. As you will see later, we also have green parts, meaning that they're plastified but not over 3%. There are orange parts, and of course, there are red parts denoting failures. So basically, this is the check that corresponds to several pages of hand calculations. Now let's move on and check the deflections for the loading of the construction stage, which is load case LE2. We can see that we have a value of 15.40 mils, which is practically identical to the value calculated in the guide, which was 17.20. We can also display the internal forces. Let's use the other load case because I have the value for this other load case. The value is 202 kilonewton meters, while in the guide, this was 206. Again, we have very good agreement in the moment. And for your reference, I have also performed this check in a global analysis software that uses beam elements. The reason I chose this software is that it allows the creation of openings to beam elements, and it does this by breaking down the beam at the location of the opening and approximating each part approximates the cross section of the opening by specially adapting the cross section properties for its member at this location. You can see it in the region of the openings. So in this case, let's go and have a look at the deformations. So for the corresponding load at the construction stage, we have a 16.4 mils deflection, and let's also have a look at the moment. Since we're running out of time, I will move back to the slides because the calculation takes some time due to the specially adapted cross sections, but I will show you the comparison. So the software gives a mid-span moment of 206 kilonewton meters. So basically, you can see that we have very, very small differences from the work example. This conclusion is very important for the application of the method, as I could roughly say that the strains which we use to check the substructure are directly related to the deflections. So having good agreement on this basic component provides confidence for the validity of the method and its generalization. However, at this point, we need to return back to the requirement that saying that the method is valid for structures that are not susceptible to buckling, and we need to demonstrate how to ensure that our structure is not susceptible to buckling. Since the analyzed substructure is made of shell elements, the code points to the relevant provisions of another part of the code, which is EN 1993-16. In this part of the code, several options are provided to the analyst for the numerical analysis of the shell substructure. These options, we employ the MNA, the materially nonlinear analysis, which is basically an analysis based on the shell bending theory, but this is applied on the perfect structure using the assumption of small deflections. To say it simply, imperfections are not accounted in this method. However, as I have already demonstrated, this is really fast. However, there is also another more advanced numerical analysis method is supported, which is the GMNIA method. This method is geometrically and materially nonlinear analysis. This is based on shell bending theory, but this is applied on the imperfect structure, which is where unintended deviations from the perfect shape are included. These types of analysis also uses assumptions of nonlinear large deflection theory for the displacement, and it also employs a nonlinear elastoplastic material law. The main issue with this type of analysis is how do we define the imperfect shape, which is something that is outside the context of this webinar, but I will provide, the code provides some rules, and I will also show you how can we define the perfect shape. However, according to this code part, every numerical analysis proposed should include a bifurcations eigenvalue check for each load level. And this is actually the way to check if the substructure is susceptible to any type of buckling effect as requested for the verification of the ultimate limit state. The bifurcation analysis is also covered in this part of the code, which is essentially a linear eigenvalue analysis. Small deflection theory applies, and the assumed geometry remains that of the perfect shell. With this type of analysis, we can obtain the lowest eigenvalue at which the shell may buckle into a different deformation mode. Like the strain limit, LBA is a generalized way of checking susceptibility to buckling for every type of buckling. Let's move back to the model and demonstrate this type of analysis. So we'll move to the LBA, just calculate it. So the LBA analysis is over. Here we can see the results of this analysis. Here, for each load case, we have a list of load amplifiers under which the loads lead to a deformation according to the corresponding buckling shape. Selecting a load amplifier, I can look to the corresponding buckling shape. And in general, for slender substructures, any critical factor under the limit of 15 should be assessed according to the provisions of the Eurocode. So let's have a look here at the lowest buckling shapes. So here we can see that we have a lateral torsional buckling. Let me deactivate the internal poses. And by moving through factors, we just see that we have higher modes of lateral torsional buckling. However, in the worked example, during the construction stage, we have a concrete floor that prevents the top flange from buckling, from moving that way. And I can enforce this requirement by moving to the operations and adding a lateral torsional restraint to the top flange of this beam. So I will not solve this again to save some time. So I will move to my project files here, and I will open solved file where I have also reinforced the first opening. Like in the worked example from the SCI, and where I can see that all these analyses are performed, and I see that I have a minimum load amplifier of 15.58, so I can accept this calculation. I can also look into the strain check. Everything appears to be gray, so the beam is fine. This, let me move back to my slides. And the conclusion from this comparison is that the results of this hand calculation and the CBFEM are practically identical. However, from the demonstration workflow, it's clear that the CBFEM calculation is more intuitive, as instead of interpreting several pages of hand calculations, the designer can visually identify the substructure parts that need to be stiffened from their deformation and strain status. Now that we stand in solid ground, we can let's see how we can safely generalize the CBFEM calculation and move to the final section of this presentation, which is overcoming the limitations of the current methodologies. In the SCI guide, there is a list of geometrical limitations that apply on the geometry of the openings and their positioning. However, it is explicitly mentioned in the guidance that openings that exceed these limits may be used, provided the design is justified by appropriate calculations based on the principle of this publication. Knowing that the CBFEM is code compliant and has very good agreement with the specific guidance makes it a perfect candidate for calculated openings that are outside the limits of this table. Also, CBFEM can be used for openings, shapes other than circular, rectangular, or elongated circular. Another limitation that is very important is that point loads should always be applied at a distance from the opening edges. This makes perfect sense, as concentrated loads create a local effect on the top equivalent T. This local effect disturbs the flow of stresses according to the theory. And although we do not consider good practice to apply loads directly above the opening, as this would lead to a solution that is not optimal, this is a case that could emerge. For example, in renovation of existing structures or due to fabrication and erection failures. So let me demonstrate this in a project I have already created. Where I'm applying the point load directly on top of an opening. However, let me zoom in and comment at this point that point loads, since these point loads are applied on a shell element, the point load has dimensions. It has a width and a length, and this actually reflects the actual dimensions of the actual source of the point load, which probably has physical dimensions. And this practice prevents stress peaks in the results. Having said that, let's move. Check, where we can see here that the local effect is obvious. We have some red parts denoting failure, and also some orange parts denoting regions close to failure, and of course some green colors. In this case, I do not even have to check for buckling because my strain is over a limit. Another issue with these beams is the ambiguity of calculation of deflections and internal forces. while in this case we had very good agreement in the calculation of deflections and internal forces, the guidance provides formulas for uniform loads, central point loads. However, modern engineering demands require the application of rather arbitrary loads, either distributed or concentrated, or to make things worse, we have an arbitrary combination of these loads. From this perspective, the numerical nature of CBFEM works very well in terms of deflection and internal force calculation. Another important limitation is that there is lack of definitive guidance for the design of the end posts, depending on the connection type. This is something natural because the underlying calculation methodology is limited. However, in the context of CBFEM, the related members are also partially modeled along with their connection types. This influences the calculation in a way that cannot be accurately accounted with the traditional Eurocode formulas contained in the guidance. Example, let me open another project variation where I have the same connection, but in this case, I have just rotated my columns. The connection remains pinned. The conditions, the boundary conditions are almost identical. However, I can see that my LBA is increased. I have a different buckling behavior. Looking at the switch the load case and looking at the deformation, I have a reduction of the deflection just by rotating the columns by 4 millimeters, which in this case is a reduction in deflection of 20%. Let me also consider another model where I have added, this is identical to the initial model, however, I added an opening near the connection and I have left the other side unperforated. In this case, I can display stresses. I'm displaying the von Mises stresses, where I can clearly see that I have a stress field disturbance in the location of the additional opening, which is not the case on the other side. And of course, we can also see that the stress field is linearized to the middle of the beam. Lastly, another limitation of the SCI guide is the evaluation of web post buckling effects in cellular beams with different web thicknesses in the top and bottom of the web. These beams can be easily fabricated from two different cross sections, and while this is a problem for the guidance, this is not a problem for the CBFEM, which can easily model such configurations. So, closing this webinar, my key takeaways is that CBFEM is a generalized method that can calculate almost any castellated beam geometry. CBFEM has very good agreement with reference calculations, and this is not by coincidence, but the reason is that it is a design-oriented method which strives for code compliance, and it can be safely used to calculate cases that are not directly covered in the guidance, or they are impossible to be calculated in this context. Before moving to the Q&A session, let me highlight that we have a list of upcoming events. Like this webinar, they're free. Some of them will be shortly announced, and you're all invited to attend. And next week, we will close our summer sessions with a course named the Assessment of Steel and Concrete Members with Discontinuity Regions, and we will return back on September with a webinar on fatigue for steel connections. So, thank you for your attention, and let's move to the Q&A session.
Okay, thank you, Kostis. I can see we have a few minutes. We have answered some of the questions that we received. We still have a few, so I'm just going to go through that. How you consider initial geometry imperfections that usually required to consider in some codes?
Well, it is very easy. Let me show you that in the LBA, when someone performs the LBA analysis, let's say that we have a factor here that is less than 15, or maybe I could attempt to open another project. This one, or let me open this one. Yeah, well, in this case, I have the configuration, but without stiffeners. So if we move to the check, and look at the load amplifiers, I can see that I have some of them are below 15, so it makes sense to identify them. And so looking at these factors, I will identify the critical buckling shapes, and I will calculate the imperfection amplitude. So here, this amplitude is calculated depending on the code context. So, for example, the Eurocode provides some guidance for the calculation of this amplitude, depending on the part that is critical for this type of buckling. So let's say that looking at the deformed shape, I can identify that this is relevant to this member. So I would go to the first part of the Eurocode, calculate the code required amplitude, and when I enter the amplitude here, then I can perform the GMNIA analysis, which will use the deformed shape, an initial deformed shape, which is the imperfect shape, that is this deformed shape, but amplified by this imperfection amplitude.
Okay, let's move on to the next question. I see there are plenty of questions coming in the last few seconds, so I'm not sure if we're going to have the time to answer all of them. Another one is, can you use the same tool to check generally the mezzanine beams?
The short answer is yes, but it would be better if you contact our support services, with a specific example, just to check if it is. But probably yes. Probably yes.
Okay. Next question: does the software cater for composite design or non-composite only?
For the moment, we perform the non-composite design, but in the future, we will also implement the composite design.
Okay. How can I apply a moment to the castellated beam?
You can apply a moment by this will be a triangular load, let's say. I'm not sure how do you want to apply it, but since we have a cell element model, a moment will be a triangular load.
Okay. Another one, Westock's cell beam software covers the fire load case. Can IDEA StatiCa cover this?
Work for fire design, and I'm not sure if we can announce it right now, but I think that in the next version we will have some, at least we will have some improvements on this front.
Okay. Can you model point moments on the beams?
Again, like I said, even the point load here needs to have some dimension due to the underlying shell model. So a point moment will be a triangular load with dimensions in order to avoid the stress peaks. This is, we do not want to have stress peaks on our models.
Okay. Hi, is it possible to have the beam pre-cambered? There's also another, there was also another comment on that, when we're talking about the challenges, there was a comment that pre-cambering is also one of them.
Well, if you want to have it pre-cambered, then you need to define the initial geometry pre-cambered. And there is not an easy way to do this, but you can approximate it by multiple line members, let's say.
Okay. I think we're out of time. There are still a few questions, so we will answer all these questions via email. But unfortunately, we have to close the webinar. It's already 10 o'clock. So at this point, I would like to thank you for attending. I hope the webinar was interesting. As Kostis mentioned, next week we have the next certification course on the design of analysis and design of members with discontinuity regions. So feel free to join that as well. It's the information is already on the iStruct webpage and the events. So thank you very much, and we're looking forward to see you in one of our next webinars.
Thank you for attending. Bye.